Let me show you how to be a good Bayesian. Change your predictions after taking information in.
I'm also wondering, if your book, when you wrote it, and especially now that you've written it, what do you see as the key takeaways for readers, and especially for readers who may not have strong background in statistics?
Mm-hmm. I hope that it's empowering in the sense that people will feel like they can use data to answer questions. As I said before, it often doesn't require fancy statistics. So there are two parts of this, I think. And one part is, as a consumer of data, you don't have to be powerless. You can, read data journalism and understand the analysis that they did, interpret the figures, and maintain an appropriate level of skepticism. In my classes, I sometimes talk about this skeptometer, where if you believe everything that you read, that is clearly a problem. But at the other extreme, I often encounter students who have become so skeptical of everything that they read that they just won't accept an answer to a question ever. Because there's always something wrong with a study. You can always look at a statistical argument and find a potential flaw. But that's not enough to just dismiss everything that you read. If you think you have found a potential flaw, there's still a lot of work to do to show that actually that flaw is big enough to affect the outcome substantially. So I think one of my hopes is that people will come away with a well-calibrated skeptometer, which is to look at things carefully and think about the kinds of errors that there can be, but also take the win. If we have the data and we come up with a satisfactory answer, you can, accept that question as provisionally answered. Of course, it's always possible that something will come along later and show that we got it wrong, but provisionally, we can use that answer to make good decisions. And by and large, we are better off. And this is my argument for evidence and reason, that by and large, if we make decisions that are based on evidence and reason, we are better off than if we don't.
Of course, I agree with that. It's like you're preaching to the choir.
It shouldn't be controversial.
A difficulty, for sure. A difficulty I have, though, is how do you explain people they should care? Why do you think we should care about making decisions based on data? Why is that even important? Because that's just more work. So why should people care?
Well, that's where, as I said, in every chapter, something bubbled up where I was a little bit surprised and said, this thing that I thought was just kind of an academic puzzle actually matters. People are getting it wrong because of this. And there are examples in the book, several from public health, several from criminal justice, where we don't have a choice about making decisions. We're making decisions all the time. The only choice is whether they're informed or not. And so one of the examples, actually Simpson's paradox is a nice example. Let me see if I remember this. It came from a journalist, and I deliberately don't name him in the book because I just don't want to give him any publicity at all. But Atlantic Magazine named him the pandemic's wrongest man because he made a career out of committing statistical errors and misleading people. And he actually features in 2 chapters because he commits the base rate fallacy in one and then gets fooled by Simpson's paradox in another. And if I remember right, in the Simpson's paradox example, he looked at people who were vaccinated and compared them to people who were not vaccinated and found that during a particular period of time in the UK, the death rate was higher for people who were vaccinated. The death rate was lower for people who had not been vaccinated. So on the face of it, okay, well, that's surprising. Okay, that's something we need to explain. It turns out to be an example of Simpson's paradox, which is the group that he was looking at was a very wide age range from, I think, 15 to 89 or something like that. At that point in time, during the pandemic, by and large, the older people had been vaccinated and younger people had not, because that was the priority ordering when the vaccines came out. So in the group that he compared, the ones who were vaccinated were substantially older than the ones who were unvaccinated. And the death rates, of course, were much higher in older age groups. So that explained it. If you put a diverse range of ages together into one group, you saw one effect. And if you broke it up into small age ranges, that effect reversed itself. So it was a Simpson's paradox. If you appropriately break people up by age, you would find that in every single age group, death rates were lower among the vaccinated, just as you would expect if the vaccine was safe and effective.
Yeah, and that's also where I feel like if you start thinking about the causal graph, and the causal structure, that's also where that would definitely help, because it's not that hard, right? The idea here is not hard. It's not even hard mathematically. I think anybody can understand it, even if they don't have a mathematical background. So yeah, it's mainly that. And I think the most important point is that, it matters because it affects decisions in the real world. So that thing have literally life and death consequences. And well, I'm glad you mentioned it, because you do discuss the base rate fallacy and its connection to Bayesian thinking in the book, right?
Yeah, I think that might be the most Bayesian part of the book. It starts with the example that everybody uses, which is interpreting the results of a medical test, because that's a case that's surprising when you first hear about it, and where Bayesian thinking clarifies the picture completely. That once you get your head around it, it is like these other examples. It not only gets explained, it stops being surprising. And this, I'll give the example. I'm sure this is familiar to a lot of your listeners, but if you take a medical test, let's take a COVID test as an example, and suppose that the test is accurate, 90% accurate. And let's suppose that means both specificity and sensitivity. So if you have the condition, there's a 90% chance that you correctly get a positive test. If you don't have the condition, there's a 90% chance that you correctly get a negative test. And so now the question is, you take the test, it comes back positive. What's the probability that you have the condition? And that's where people kind of jump onto that accuracy statistic, and they think, well, the test is 90% accurate, so there's a 90% chance that I have, let's say, COVID in this example. And that can be totally wrong depending on the base rate, or in Bayesian terms, depending on the prior. And here's where the Bayesian thinking comes out, which is that different people are going to have very different priors in this case. If you know that you were exposed to somebody with COVID, 3 days later you feel a scratchy throat, the next day you wake up with flu symptoms. Before you even take a test, I'm going to say there's at least a 50% chance that you have COVID, maybe higher. Could be a cold, so it's not 100%. So let's say it's 50-50. You take this COVID test, and let's say, again, 90% accuracy, which is lower than the home test. So I'm being a little bit unfair here, but let's say 90%. Your prior was 50-50. The likelihood ratio is about 9-1. And so your posterior belief is about 9-1, and which is roughly 90%. So quite likely that test is correct, and you, in this example, have COVID. But the flip side is, let's say, you're in New Zealand, which has a very low rate of COVID infection. You haven't been exposed. You've been working from home for a week, and you have no symptoms at all. You feel totally fine. What's your base rate there? What's the probability that you miraculously have COVID? 1 in 1,000 at most, probably lower. And so if you took a test and it came back positive, it's still probably only about 1 in 100 that you actually have COVID, and a 99% chance that that's a false positive. That's the usual example. It's probably familiar, but it's a case where if you neglect the prior, if you neglect the base rate, you can be not just a little bit wrong, but wrong by orders of magnitude.
Yeah, exactly. And it is a classical example for us in the stats world, but I think it's very effective for non-stats people because that also talks to them, right? And it's also that the gut reaction to a positive test is so geared towards thinking you do have the disease that I think that's also why it's a good one.
Let me show you how to be a good Bayesian. Change your predictions after taking information in.